Electrostatic potential is an integral of electric field, and we put the negative sign on it. It is based on the fact that electrostatic force is a conservative force. If a force is conservative, then there exists a potential energy that is independently obtained by the path of the integral. That means the potential energy depends only on the information of endpoints, starting and finishing point. However, the initial point dependence doesn't matter because it is a constant. And if you take the derivative and put the negative sign on it, then you can find the force. We have a more convenient concept that is called electric field that is identical to electrostatic force, except that the strength of the force is divided out already. So effect of the test charge has been factored out, and this electric field is assumed to have the information of charge distribution surrounding the test charge. So in that case, the electric field is obtained by taking the minus derivative of the potential. Sure, the potential multiplied by charge will be the potential energy. We first consider the case for the single point charge that is the single source at point somewhere, and we want to measure the potential. Eventually, we are interested in the electric field, but we know the electric field is a vector and electrostatic potential is a scalar. Scalar has a single component and vector has three components. That's the reason why we prefer potential to the electric field. At the end of the day, we will take the minus the gradient to find the electric field out of the potential. So we assume that we know how to compute the potential for a single point charge placed at the origin, and the field point is where we measure the electric field. We denote capital R by the difference, the starting point. This is the starting point, that is the position at which the source Q is placed, x prime. And what we measure, the electric field, is at a field point that is a P. This is a field point. The electric field is measured. Because the electrostatic force is central, we always need to find the displacement vector from the source to the field. This is the capital R. Okay? The capital R is always x. X is the field point subtracted by the position of the charge. Usually, this charge is distributed over a large volume, so we need to integrate. Anyway, we decomposed into Cartesian coordinates, and this is x, y, z components. The magnitude of this distance is the square root of the sum of the squares of the Cartesian coordinates. Once you know this value of the distance between the field point and the source charge, then we determine this potential and then insert this potential into this formula minus gradient. Gradient is E1 hat, x1 derivative, and so on. So we want to find this gradient. However, this expression is in terms of the distance, and that is again a function of positions. So we have two-step structure. So in that case, we usually make use of the chain rule to find out the derivative. First, we want to find a simple formula for the derivative of the potential with respect to this scalar instead of each coordinate. It is a function of 1 over r. Its derivative with respect to the same variable is a trivial 1 over distance squared and put the negative sign on it. And then eventually, we need to evaluate the partial derivative with respect to each coordinates of a field point. Derivative should be given for the field point, not for the source points. Derivative of the field point can be made. This is 1/2. This represents the square root. We take the derivative, and it's something's power is 1/2. We bring in this 1/2, and 1/2 minus 1 will be the power of the derivative. So it becomes minus 1/2. Inside is kept the same. We make use of the chain rule. So what we want to do is to take the derivative of inside with respect to x1. So this one vanishes and only this contribution survives, and that is a factor of 2, and then this. So 2 cancels, and what we have is this is in the denominator because of the negative sign, and the numerator is the difference x1 minus x1 prime. In a similar manner, we can compute all of the contributions for Cartesian components. So using this result, I copy in here and replace x1 and x1 prime with 2 and 3. Remember, we have negative sign on it, and we have negative sign on it. These two negative signs cancel, and finally we do not have negative sign. So what we find in here is identical to the Coulomb's law. Next, we considered a charge Q distribution uniformly distributed over a hemisphere. This is a full sphere, and I cut the upper part of the hemisphere, and the remaining part is just the lower hemisphere only. And source charge is distributed uniformly, and then I have a field point. This is a field point. O is equal to P, and we have a radius R. What is the electrostatic potential at point O? Okay, so X is the position vector of the field point, and my field point is at the origin, whose vector notation is 0. What we have to do is integrate over the surface, and we have small dq, and we know all of the distance from this source to the field point is exactly the same as r, everywhere r. So in this integral, I can pull this r out, and the trivial integral everybody can evaluate without complication. It is q. So this is the electrostatic potential at the origin. Next, we consider a more complicated case. I have chosen a field point along this straight line that is normal to this plane. And our new field point is a ZE3 hat. That is a new field point. It is not at the origin anymore and shifted somewhere around here. And I have a new coordinate dependence Z. Then everything is the same except that the distance should be modified. We know that any point on the spherical surface can be represented by a polar coordinate system that has a polar angle theta dependence and azimuthal angle phi dependence. When you square, and sum them all, we'll find everything becomes a sum becomes 1. So this is a unit vector, and this is a radius r. And the range of this r is fixed. Range of theta is because our theta is measured from the positive z-axis. So this theta begins at 1/2 of pi and it ends up with pi. So physical range of polar angle is from 1/2 pi to pi. And then azimuthal angle is integrated over to pi. So using this information, and we have x coordinate. This depends on the z component only. As we have done with the previous calculation, we can find out the surface charge density. This is charge divided by area. 4 pi r squared is the area of the full spherical surface, but we cut it off into 1/2, so we have 2 pi r squared. And if you want to compute dq, infinitesimal charge, then charge density multiplied by area. Polar coordinate area can be expressed in terms of r squared and d cosine and d phi. So r squared cancels, and only azimuthal angle and the polar angle dependence abides in here. When you compute the distance between the charge and the field point, everything is simple except that z components, and this comes from the field point dependence, x dependence, and these are all from x prime dependence. So x squared, y squared, z squared component are summed, and then we take the square root. Because it is trivial, it becomes a sine squared, and when we expand this is cosine squared, cosine, and z squared, and so on. And cosine squared and sine squared merges into a unity, and at the end of the day, we find the distance r between the field point, some field point, and a charge. This is capital R. This one is expressed in terms of this. Now we evaluate the integral over this hemispherical surface, and that is not really difficult. We have this one in the denominator. We have parameterized the integral into cosine and phi integral. And we know this phi dependence does not appear in the integrand, and this one is a trivially 1 because we have 2 pi in the denominator and constant integrated over 0 to 2 pi, so we don't need this. So only polar angle dependence is our problem. Okay, why don't we substitute alpha for the argument of the square root, and we remember cosine theta runs from -1 to 0. What are the endpoints? If I substitute cosine equals -1, what I find is it is completely, there's the square. This, we can complete the square. When cosine theta becomes 0, this term vanishes. So square plus square. So we now we rewrite this. This one was replaced with alpha, and alpha runs from here to there. So substitute these values, and it becomes this. For fact, what is the original factor of 2? Because I have replaced the whole thing as alpha, the change in cosine has additional factor -2rz. -2 appears here. And the high school student can integrate this one. This is a d square root alpha. And then final result is nothing but this. Okay, so our integral table is not really complicated.